Okay, good afternoon, everyone. We are very happy to have as our speaker today Nati Seiberg, but before that, I would like to ask...
One moment, please.
Okay. I would like to ask, first of all, Professor David Horn, who was a PhD student of Yuval and was also a teacher of Nati Seiberg, to say a few words, please.
Okay, welcome everybody, in particular Dvora, Yuval's widow, who honored us here today. It is 2 years since Yuval has passed away. It's hard to believe that we live all the time without him. Now, Yuval is, for many of us here, somewhat of a mythological figure, although he was very much with us at present and in the past. And I would like to recount a few items from the years when he returned to Israel and founded the School of Physics. As you all presumably know, he was kind of a phenomenon at a very early age. He started studying at the Technion at the age of 15. But then the War of Independence came and he was busy with a military career. And he resumed studies much later, in the late 50s, and started his academic career in 1961 when he finished his PhD at Imperial College in London. This PhD of his in 1961 was a masterpiece or a very important breakthrough in physics. This was SU3 symmetry theory of particle physics, and we'll return to this topic. He returned to Israel and he founded this School of Physics 3 or 4 years after returning to Israel. And in fact, the School of Physics bears his marking since then. And for many years he was chairman of the school. Then at some point he became president of the university. But he was always a very energetic person and always wanted to have 2 or 3 things running in parallel. So doing only science, or science usually was more than physics, but doing only physics or doing only the administration was not enough. He decided also to go into politics. So at the late 70s, he went into politics. Many of the audience know the story of the Tchia party, and he became Minister of Science. In 1983, he was Minister of Science, and he left politics around 1990. And I tell all this story to say that there were kind of 3 pillars in these years of the formative years of this School of Physics, and in some sense his academic career and other careers in Israel. And these pillars were his academic work in theoretical particle physics, his various administrative work, and the School of Physics bears witness to his success in this direction, and his political work. Now, in these various fields of life, he also had disappointments. We know the story that he did not get the Nobel Prize, and that was a very sore point with Yuval. And in fact, his work, the 1961 PhD work of Yuval, was a breakthrough in theoretical particle physics. It was also quoted as part of the reasons why Gelman got the Nobel Prize, but Yuval did not get it, and as I said, it was a sore point with him. politics was also a sore point. I think he was disappointed with politics. Dvora can tell it, and he left politics, in fact, with a broken heart and even a broken pocket in some sense. But the School of Physics, that is the third pillar, he loved the School of Physics, and the School of Physics loved him. And we had, throughout the years, we had many celebrations with Yuval. Every round birthday, we had a conference or something very special done for him. The last opportunity of this kind was his 80th birthday, which we celebrated 2 years ago, shortly before he passed away. And many of us remember this time, and the love of the School of Physics is seen today in terms of this particular seminar that was created in his memory, and it will be an annual seminar going on from now until eternity. Our first speaker in this seminar, the first occasion is today, and the first speaker is Nati Seiberg. Where is Nati? Hi, Nati. You're standing, not sitting. And Nati is interwoven in some sense in this history, because he was a student in this school. Even before it was called a school, it was a department at the time. And in 1977, he finished his BSc in this School of Physics. He was in the Atuda at the time. He went back to do his army service, and in 1982 he finished his PhD at the Weizmann Institute. Then he, in fact, joined the faculty of the Weizmann Institute as an associate prof and then a full prof, but around that time, late 80s, Rutgers brought him to the US, and he became a professor at Rutgers University, and later on he left Rutgers for the Institute for Advanced Study, where he's a professor since 1993, right, or 1994 or so. He is often quoted as an example of a very bright Israeli whom we lost to the US. And in fact, in an article, I think it was Haaretz or some other newspaper, about a month ago, with a list of many successful Israelis in the US, he was quoted as one example. He's certainly very successful, very well known in the field, supersymmetric gauge theories and string theory. Well, the word string theory, I think, is well known also to laymen outside physics. So Nati is one of the world experts and the world leaders in this field. And although he left Israel for the US, we are happy that he's still a frequent visitor in Israel. So we see him quite often, and it's for us an honor that he is the one who gives this lecture. I mentioned already SU3 at the beginning, and one of the things that we learned from Yuval is the importance of symmetry, and that is something that we teach our students in theoretical physics ever since, and it is befitting that also this talk will be on a different symmetry, the supersymmetry, and it's breaking, but it's still symmetry. So Nati was awarded a few prizes, in particular the Danny Heinemann Prize. And as I said, he is a very well-known figure, and we are very happy to have him here and to be the first speaker in this annual event. Thank you.
I would like to invite Yuval Neeman and Professor Yaron Oz, the chairman of the School of Physics and Astronomy, to award this year's prizes, which are part of the memorial ceremony. Please.
Yuval was also the founder of the Weiss Observatory. It's the only astronomical observatory in Israel which does research. And the recipient of this year's scholarship, Yuval Neeman Scholarship, is Avi Sporer. Where is Avi? Avi is a student of Professor Tzvi Maze, and he's a PhD student, but he's already done major contributions to two fields. One of them is non-galactic astronomy, where he was involved in the discovery of a black hole in a binary star some 2 million years away. This was published in Nature and received also a lot of echo in the media. The second field he's still working on, and he also made major contributions, are stars outside the solar system. He was involved in the discovery of one and the studies of properties of another one, of planets, sorry. I translated wrongly from Hebrew. Well, to those who don't know what the difference between star and planet is, the ones that burn or don't burn. Yeah, okay, so Avi has already 17 papers, and he's definitely 17, so we should hire him already. And I hope he will have many more during his PhD. Congratulations.
Okay, so now I would like to invite Professor Nati Seiberg to tell us about supersymmetry and its breaking. So we have
Thank you. רק לקה, יש לי קול חזק. It's a great honor to give this talk in memory of Yuval Neeman, whom I have admired since my childhood. It's also a great pleasure to visit my many friends and colleagues here and interact with them. Finally, Tel Aviv University brings me good memories from the time I was an undergraduate student here. Here is where I started my physics education and where many of my views about physics were set. For example, David Horn, who made the introduction today, he exposed me to modern physics. It was a course for first-year undergrads, Introduction to Modern Physics, and it was a great joy. It is a tradition in such talks to start by saying something like, the first time I met Yuval Neeman, etc., etc. I thought it would be original to start by describing the last time I met him. It was during the 2005-2006 Jerusalem Winter School, a school which Yuval had initiated. The school organizers had arranged for a session honoring Yuval on his 80th birthday, and I was asked to say some words. I thought it would be appropriate to repeat them here. Most people have no career. Fortunate people have a career. It is rare to find people with 2 careers. Yuval had 3 or 4 careers, depending on how you count. He was a successful general and a military attaché. He was a very influential physicist, making groundbreaking discoveries. He was an effective academic administrator who created a lot of the existing academic structure in Israel. And he was even a politician and a minister. Yuval had many students who themselves had many students who had themselves more students. He liked to refer to them as his scientific children, grandchildren, and even great-grandchildren. Many members of this dynasty are here in the audience today. I'm not talking about this audience, I'm talking about the audience there. I am proud to be one of Yuval's scientific grandchildren. The talk today is about recent developments and possible future discoveries along the road that Yuval started paving, which was described here by Professor Horn so eloquently. He made many contributions in particle physics, a field whose next chapter will be uncovered soon. He also explored the theoretical idea of supersymmetry, which might be discovered in the near future. So the purpose of this talk is to tell you what supersymmetry is, why we think that supersymmetry might be discovered in the near future, and finally discuss some of the recent developments in supersymmetry. Now, the talk has 3 parts, which are not completely logically independent, but if you feel completely lost in one of them, it's not a prerequisite for the second one. And the first and second are not prerequisite for the third. So if you want to live in the middle, you might lose something. So this is the LHC, the Large Hadron Collider at CERN, Geneva, just for the scale, whoops. Just for the scale, this is the accelerated tunnel. This is the Geneva International Airport. Whoops, what is this? So this is the accelerator. It's quite a big experiment, and it's going to become operational soon. And there's a question of what the LHC will find. So, of course, we don't know, but this is really the time to place bets, kind of about a year or two before we start getting the results. So I prepared here a list with increasing odds. So I'll start with the least likely one and going on to the more and more likely one. And this is my own prejudice, and if anybody wants to place bets, I'd be happy to do it after the talk. So I'm going to assume throughout this presentation that the LHC works fine. I'm not an experimentalist. I trust the experimentalists that they know what they're doing. The machine will not break, and they will measure things correctly. I know it's not a valid assumption, but let's do it anyway. The first thing that can happen is nothing. So they turn on the machine works fine, and they find nothing. This is extremely unlikely. There's at least one particle that we expect to find, and which I'll soon say more about it, which is the Higgs particle. Without the Higgs particle, unitarity is violated. So quantum mechanics is wrong. So this would be extremely interesting if this is the case, but let's dismiss that as extremely unlikely. So at the very least, we have very good reasons to believe that something is there, and it will be discovered, because otherwise we have to revise quantum mechanics. Second possibility is the absolute minimum which is needed in order to have only quantum mechanics. In other words, we'll find only the Higgs particle. This is a very boring possibility. The standard model, which Yuval was one of its founders, will turn out to be correct, and there will be nothing beyond that. This will be extremely disappointing. It will also point to a question of unnaturalness and whether the universe is entropic, issues I'll discuss later in the talk. I find that, again, somewhat unlikely. A more likely possibility is that some new particles will be discovered. Throughout the 20th century, many elementary particles were discovered. Again, Yuval made a major contribution in classifying them, and people understood that they are quarks. There's still a large number of quarks, and it's quite possible that there are more particles. There's no reason to believe that the list ends here. So there could be more particles, but without any new concept. This is, again, I think, more likely than just the Higgs, and I'll say later why I think that this is a logical possibility. Going down the list, things which are more plausible, that the universe is natural, and I'll define natural more precisely later. And this falls into two categories. Again, my prejudice is that the least likely of the two is an idea called technicolor, that the universe has more dimensions. This, of course, will be quite exciting if the machine discovers that space has more than the three spatial dimensions that we know about. A more likely possibility is supersymmetry, which I'll discuss in a minute in much more detail. And this is the idea that the universe has more dimensions, but they're fermionic. And again, I'll make that more precise. This is the thing I really think is the most likely. The most likely possibility is that something we have not thought of. Nature has always been a lot smarter than the people who explore it, and therefore it could be a surprise. So we're really expecting something really interesting. This is a menu of possibilities, and this is a menu of possibilities. We don't know which of them will turn out to be right, but I think it's quite clear that it's going to be very exciting. So from a pragmatic point of view, I view supersymmetry as the most conservative and the most conventional possibility. As I said before, this is a topic that Yuval really liked. He wrote some of the interesting papers, many interesting papers about supersymmetry. So in this talk, there will be three parts. In part number one, I'll define supersymmetry. I'll give several different definitions of supersymmetry. In the second part, I'll motivate the claim of why this is the most likely possibility. And in the third part, I'll discuss some of the recent developments in the field. Supersymmetry has 3 presentations, and you can take whichever of the 3 you prefer. Some of them are more abstract than others. I'll first list them, and then I'll spend a slide or 2 on each of them. First, this is a symmetry which pairs bosons and fermions. It pairs particles with integer spin, which are bosons, with particles with half-integer spins, which are fermions. This celebrated SU3 of Neeman is a symmetry which does not change the spin of the particle. So this is an extension of the notion of ordinary symmetry. The second presentation is an extension of the Poincare symmetry. And the third presentation is that supersymmetry is an extension of the ideas of space and time. There are additional dimensions which are quantum mechanical. The ordinary dimensions that we are familiar with, x, y, z, and time, are really bosonic, and they are classical. We can measure distances. In fact, people knew about these dimensions long before they knew about quantum mechanics. Fermionic dimensions do not exist in classical physics because fermions don't exist in classical physics. So the possibility of supersymmetry is an extension of our ideas of space and time, where we append to the ordinary dimensions new dimensions which are intrinsically quantum mechanical. Now, these are 3 presentations of supersymmetry. Different people have different prejudice or different priorities, which of the 3 they prefer. So let me say a few words about each of them. First, an extension of the Poincare symmetry. The Poincare symmetry is a symmetry of translations and rotations and boosts. We have an object here. We can shift the lab, perform the experiment not here but elsewhere, and get the same results. This is generated by an operator of translation, called P. What is this? An operator of translation called P. So one way to present supersymmetry is to say that there are other generators denoted by Q, and they satisfy anti-commutation relations. So the anti-commutator of Q with this Q is the momentum P. Notice that this is an anti-commutator. Non-ordinary symmetries are associated with commutation relations, like rotation symmetry has commutation relations. Commutation relations arise in quantum mechanics by generalizing the Poisson brackets of classical physics. In classical physics, we have Poisson brackets. In the quantum theory, we turn them into commutators. We can't have anti-commutators in classical physics, and therefore, such a symmetry is intrinsically quantum mechanical. It does not have a classical analog. So this is the first presentation of supersymmetry. The second is in terms of the spectrum. Translations relate an object here to an object here. Simply shift it. Similarly, supersymmetry generated by Q relates one particle to another. But since Q is fermionic, it's an anti-commuting object, the symmetry pairs a fermion to a boson. So Q acting on a fermion gives a boson, and Q acting on a boson gives a fermion. Similarly, it changes the spin of the particle. So in that's the novel thing about supersymmetry. It changes the spin and changes the statistics. So this is the second presentation of supersymmetry. The first is in terms of extending the Poincare symmetry, and the second is in terms of relating bosons and fermion. The third presentation is a little bit more abstract, and none of these presentations are really essential for the rest of the talk. So it's good to have them so we know what we're talking about, but if you find that too abstract, don't panic. So we think of new quantum dimensions which are fermionic. So imagine we have some field like the electric field, phi, which is a function of space and time denoted by x. We add some anti-commuting variables, theta, and then Q implements translations in theta. P implements translations in x, and Q, the supersymmetry transformation, implements translations in thetas. Since theta squares to 0 because it's fermionic, then if we expand this object in a power series, the power series terminates after a finite number of terms. These ordinary functions of x are like the electric field, magnetic field, etc. These should be viewed as these different particles. So the bosons and the fermions that I talked about before are these different functions. and I apologize for being too abstract here. So this is the end of my first part of what is supersymmetry. Now that we all know what supersymmetry is, we can ask, why do we believe that this has anything to do with nature? So in the coming slides, I'll move to the second part, and I'll list motivations for supersymmetry. And there will be three main motivations. Every one of them will be 1 or 2 slides. Dark matter, coupling constant unification, and the hierarchy problem. These are the three main motivations for supersymmetry. And there are also other motivations, which are somewhat less convincing. The first is string theory. In string theory, supersymmetry arises very naturally. In fact, supersymmetry was first discovered in the context of string theory. So it must be present as a symmetry at very high energies around the Planck scale. Now it might or might not be present at low energies, energies which are accessible at the LHC, but given that the symmetry is there, at high energies we can hope that it's also there at lower energies. The previous motivations I mentioned, and I'll elaborate on them soon, tell us that in fact we expect supersymmetry to be present at the TV range of energies, energies which will be explored by the LHC. The second reason is also somewhat indirect. Supersymmetry is a beautiful theoretical idea which has already led to many applications both in mathematics and in other branches of physics. And historically, whenever we had a new idea which was good, say in mathematics, it was also good for physics. Calculus is one example. I think there are good reasons to believe that supersymmetry is another. And in fact, many of the recent developments in mathematics really stem from ideas associated with supersymmetry. And if supersymmetry is so useful, maybe nature is also kind enough to use it. So I'd like to stress that none of these motivations is really ironclad, but I think it's somewhat compelling. So let me spend a few more slides about the more solid ones. The first is the topic of dark matter. So recent astronomical measurements tell us that only a small fraction of the matter in the universe is in terms of particles we know of. If we look at the total mass of matter in the universe, and I'm excluding here the dark energy, just out of the matter, only 18% of the matter in the universe is made out of the ordinary matter and particles we know of. The vast majority, 82%, is something else. It's dark. And this is the picture of WMAP, and I'm sure you heard many colloquia about WMAP. I won't elaborate on that, but there is complete consensus that this is right. 82% of the mass of the universe is dark. So what is this dark matter? The leading candidate for this dark matter is what is referred to by the acronym WIMP. These are weakly interacting massive particles. So these are particles which do not interact with electromagnetism, and therefore they appear dark. So they don't couple to photons, and therefore these particles are not visible to us. However, they are massive. So if we have such massive particles which are neutral, they do not interact with photons, but they can bend light, they can exert gravitational force, and as such, they can be indirectly detected as dark matter. These particles should also be stable. They have to be stable because otherwise they would decay and won't be around to affect astronomical measurements. And so there's a very simple kind of back of the envelope calculations which says the following. If we want such neutral particles to be the dark matter, and their interaction have some strength, say like the strength of the weak force, I can easily give a factor of 10 here or there, then we can calculate the mass of these particles. And the mass has to be between 100 GeV and 1 TeV, maybe 10 TeV, but this is the order of magnitude. This is an extremely interesting calculation, because what goes into it has absolutely nothing to do with particle physics. All the numbers which go into these calculations come from cosmology. It's the Hubble constant, the age of the universe, the amount of dark matter, and so forth. This calculation does not know what the energy scales of particle physics are. It is not an input in the calculation. And this calculation certainly does not know what energy scale the LHC will explore. Yet, it predicts a mass which is right where the LHC will be most powerful, somewhere around 1 TeV. So, as I said, if this is the origin of the dark matter, if the dark matter is indeed made out of such WIMPs, then we have independence of supersymmetry. This argument has nothing to do with supersymmetry. It tells us that there must be new stable neutral particles around 1 TeV. So when I said earlier that finding just the Higgs is not completely satisfactory for the LHC, and I think a more likely possibility is that there are more particles, there are additional particles that the LHC will discover, this is what I had in mind. That there are totally independent arguments which have nothing to do with particle physics, which tell us that there must be new physics that the LHC will explore. And it will be quite interesting if the LHC indeed produces this dark matter. So the LHC can become a machine which is like a factory of dark matter particles which will be discovered in the lab. This will be extremely exciting, of course, making 82%. Sorry?
How will you see them?
This is a very interesting question. This is an experimental question, and there are very clear signatures. The simplest way this will happen is that you create a particle, a massive particle, which will decay. And it will decay to a dark matter particle that will go here, and ordinary particles which will go here. So we'll have this collision of protons coming this way, creating an object here, with a shower of particles going in this direction, and nothing to balance it in the other direction. So that is called missing energy. We'll say that something will have to go in the opposite direction. And by repeating this experiment many times, in fact, the LHC will do it trillions and trillions of times, you will eventually explore all the properties of this dark matter particle, and you can nail down many of its properties. So particle physicists know exactly how to do that. In fact, the neutrino was discovered exactly like that. This was missing energy. So C is not necessarily with photons. Any more questions? I would encourage questions.
You put it in a little bit of particle physics by saying electroweak strength.
No, the strength could be easily a factor of 100. This is just the alpha, that the strength is a
It couldn't be much bigger.
factor of 10 here or there. So, as I said, between 100 GeV and say 10 TeV. Yeah.
A fellow in Vancouver University named Princeton says that there's another way to explain all this about producing dark matter.
Okay, so I'm glad you asked that. First of all, Bekenstein is at the Hebrew University. First of all, Bekenstein is at the Hebrew University. Second, the person who first said that is Nati Milgrom, who is at Weizmann Institute. And I really hope they're right, because it will be very exciting. But I'm not a dark matter expert, but the majority of the community, and I think they will agree with that, do not believe this possibility. And since I'm not an expert, I leave it at that. The statement is that there is an alternative to dark matter which involves modification of Newton's law. This would be extremely interesting if it's right. I think it's a very long shot, mostly based on conversations with experts who looked into it. But I'm not here to defend one position or another. And I gave this talk in front with Nati Milgrom sitting in the front row last week, and he agreed with that statement. WIMPs in SUSY. So far that has nothing to do with supersymmetry. It's just that WIMPs are the leading candidate for explaining dark matter. It's 80% of the mass in the universe. But with supersymmetry, this is extremely natural. Assuming supersymmetry, particles are paired. For every boson there is a fermion. For every fermion there is a boson. So the electron's partner is called selectron, and the photon partner is called photino, and so on and so forth, the whole zoo of new particles. And the lightest superpartner is typically stable. Typically this is the photino. And it satisfies all the requirements to be a WIMP. It's neutral. It's the superpartner, say the superpartner of the photon. The photon is a neutral particle. It's stable. It's the lightest one. It has nothing to decay to. And it has some weak interactions, but no electromagnetic interaction. So this is not something that we add to the theory. The theory automatically has such a particle. So if supersymmetry is indeed right, we automatically have such a stable particle, a WIMP, at the right energy scale, the energy scale that the LHC will explore. So ironically, the dark of the mass of the universe, this missing energy, this dark matter, can consist of particles which are the supersymmetric partners of the particles of light. So the particle of light is the photon. It's related by supersymmetry to the dark side of the universe. So this is the first argument for supersymmetry in the TeV range, the existence of dark matter. This is very natural in the context of supersymmetry. The second argument in favor of supersymmetry is the idea of coupling constant unification. If we measure the various forces in the standard model, so we know of three forces: the strong force, the weak force, the strong force, the strong force, the weak force, and the electromagnetic force. These are the three elements of the standard model. And they have their strength, so it's better to plot one over the strength. So this is the strongest force, then the next one in the list is the weak force, and then the electromagnetic force. And the strength of the force depends on distance. So if we take two particles, the electromagnetic force between them, Coulomb's law, is 1 over r squared. But in addition to the 1 over r squared, the coefficient out front, Coulomb constant, this constant depends on the distance, very slowly through logarithm of the distance. So we can plot 1 over the strength as a function of the log of the energy, take the measurements here at this energy, around 1000 GeV, or 100 GeV, where these numbers were measured, and extrapolate them to higher energy. This calculation was first done by Georgia, Quinn, and Weinberg in the 70s. And with the accuracy of the strength, the known strength at the time of the strong force, these three lines met at a point. So this is an extrapolation over 15 orders of magnitude. It's quite bold. And the three numbers really met at a point. Sorry?
And it's linear.
It's linear extrapolation. This is what theory does. It's linear in log scale. So, well, that's the calculation they did. And at the time, the strength of the strong force was not known very accurately. The three lines met at the point, and this was quite an interesting and surprising result. Today, we know the strength of the strong force much more accurately. These two numbers were known accurately at the time. So we know this number much more accurately, and they clearly do not meet at the point. However, if all we say is that there is supersymmetry in the TeV range, this linear extrapolation comes with a different slope. The slope is determined by the number of particles. We have more particles, the slopes are different. If we just repeat this calculation, this was first done by Dimopoulos and Georgi, again in the 70s or maybe 80, and the lines meet at the point, and this is incredible accuracy. This is better than 1%. This is an amazing success, and since then, the measurement here of the strong force became better and better, and this is still consistent. There are two attitudes about that. One is that's really significant, and I'll elaborate on that soon. The other is that two lines always meet at a point. So it's only that the first and the third line meets at the same point, so it's only one coincidence. And the history of physics is full of such coincidences. For example, if we look from Earth at the Moon and the Sun, they look like they're the same size. And we all know very well what this coincidence did to the history of astronomy, started with the Babylonians and for centuries later. So it could be that we are fooling ourselves here, and this is just a coincidence that one should not pay too much attention to. I think that's not the case. I think it's quite significant that these three lines meet at the point. Because what it means is that here at low energies, around 1000 GeV or so, or 100 GeV, these three forces look distinct. But at high energies, around 10 to the 17 GeV, these three forces have the same strength, and the reason for that is that they're really the same force. So nature does not have three distinct forces, but has only one force here, which manifests itself as three different forces at lower energies. Again, the history of physics is full of such situations. Maxwell unified electricity and magnetism as being two different manifestations of the same electromagnetic force. Weinberg and Salam unified the electromagnetic and the weak force, and they got the Nobel Prize for that. And this is just the next step in the same direction direction that physics progresses, of unifying what appears like distinct ideas. So this is called as grand unification. Oops, how do I do it? So with supersymmetry, the strength of the distinct forces, the distinct gauge interactions become equal at around 10 to the 16, so 10 to the 17 GeV. And that suggests that they could be unified there to a grand unified group. In addition, such unification of forces also explains many of the features of the quarks and the leptons, many of their quantum numbers. So if these lines indeed meet at the point, we get a lot of explanations to some of the peculiarities of the quarks and the leptons. So that's another reason to believe in grand unification. Conversely, if supersymmetry is indeed discovered, it will tell us that this idea of unification of forces is clearly right, and it will give us a window to very short distances, or conversely to very high energies. It will allow us to extrapolate freely through such 12 or 15 orders of magnitude. So this is the second big motivation for supersymmetry. One is dark matter, the second is unification of coupling, and the third is again more abstract. It's known as the hierarchy problem. This is a problem that was first raised by Dirac early in the 20th century. Dirac knew of the Planck scale, invented by Planck. He knew about the proton mass, and he noticed that the ratio between them is 10 to the minus 19. And Dirac asked himself, where did this small number come from? In physics, we never have such small numbers without an explanation. In physics, we often have dimensional analysis working quite well. So an example I like to say, I'll throw this pointer and catch it. Just how high does the pointer go? Well, we know the formula. There is the acceleration of gravity, g, and there is the time, t, the time it went up. So on dimensional grounds, the answer has to be gt squared. This, I haven't put any dynamics in, I just said this is dimensional grounds. The actual formula has a half in front of it. But this is a number of order 1. And that's the way physics works. We do dimensional analysis, and then we throw in, there might be a pi, or a pi square, or 1 over pi square. We never throw in 10 to the minus 19. It's never the case that we do dimensional analysis, and then the answer multiplies that by 10 to the minus 19. Dirac was very disturbed by that, and that's come today, is called, we say that this is just unnatural. Where did this small ratio come from? It could be that this is just an aesthetic problem. It could be a very deep problem. Dirac thought it was deep, so I think we should follow him. There is a modern version of this problem. In fact, today we understand where this small ratio came from, but there is a counterpart of that, relating the mass of the W and Z bosons, which are about 100 GeV, to the Planck scale. These are 17 orders of magnitude, and we could ask ourselves, where did this come from? So unlike this ratio, which we sort of understand, we do not understand this ratio. So we could ask, where did this ratio come from? And again, this could be just an aesthetic problem. But in fact, the problem is more serious. This hierarchy is not stable in quantum mechanics. Quantum mechanics works, the dimensional analysis works in quantum mechanics much better than it does in classical mechanics. Classical mechanics, we can put particles in unstable situations. In quantum mechanics, we can't do that, because there are always quantum fluctuations, and quantum fluctuations destabilize things which are unstable. So such a hierarchy, even if we put it in by hand, is not stable quantum mechanically. And quantum fluctuations tend to restore dimensional analysis and ruin the hierarchy. A well-known example is level crossing. If we turn parameters and two levels try to cross in quantum mechanics, in fact the levels repel, and we don't have two levels which are too close to each other because they repel each other. In terms of condensed matter, this is like tuning to a critical temperature without a symmetry. So imagine the world is very close to a critical point. 10 to the minus T minus Tc over T is 10 to the minus 19. In fact, the relevant number is that we have to square that. So we had 17 before, this 17. The relevant number is really the square of that, so it's 34. So the analogous thing in condensed matter is that we have a critical point in the lab, we turn the knob, and we stop 10 to the minus 34 before the critical point. I think everybody would agree that this is unnatural. No, we don't do that. Even the best experimentalists cannot tune to 34 orders of magnitude before the critical point. Not only that, the whole system, as I said, is quantum mechanical. And in quantum mechanics, we cannot have such accuracies because of quantum fluctuations. So this is the technical aspect of this hierarchy. So we have to understand where this ratio came from and why it is stable. Supersymmetry comes to the rescue. Supersymmetry has these bosons and fermions. I've already said that before. And the quantum fluctuations of the bosons slightly cancel the quantum fluctuations of the fermions. So at least this technical aspect of the hierarchy, that quantum fluctuations tend to restore dimensional analysis, this aspect of the problem is solved in supersymmetry. So this addresses the technical aspect of this naturalness. The aesthetic one of where this number comes from, I'll come to in a minute. However, there is immediately a difficulty. Supersymmetry must be broken. In other words, we found the electron, but we have not yet found the selectron. So what am I talking about? We have the electrons and the quarks and the photons, etc. We have not yet seen even one of the superpartners. So where are these superpartners? Well, the cheap answer is that, well, they're heavier. They are heavier. We haven't discovered them yet. And maybe the LHC will discover them. But if the superpartners do not have the same mass as, say, the ordinary particles, the electron and the selectron do not have the same mass, the symmetry cannot be exact. The symmetry has to be broken. And the phenomenon we have here is a phenomenon of spontaneous symmetry. And again, I give an example of statistical mechanics, the example of a ferromagnet. In a ferromagnet, all the spins can point in one direction, or all the spins can point in another direction. Well, in fact, the spins point in a particular direction, and this is the phenomenon of spontaneous symmetry breaking. It doesn't matter where they point to. If we look at low energies around the direction of the spin, so we make small fluctuations, we do not see that there is an entire symmetry for rotation. We have to go to higher energies or shorter distances to restore the symmetry. So the idea is that supersymmetry is actually an exact symmetry, but the symmetry which is spontaneously broken. So here I say it again, the superpartners are heavier than their counterparts. Hopefully they will be measured at the LHC. And therefore supersymmetry must be broken. And then experimentally, the details of how supersymmetry is broken and how the supersymmetry breaking is mediated or fed into the ordinary particles can turn into prediction about what the spectrum of superpartners are. So if we were very smart, we could understand how supersymmetry is broken, how this information is fed to the standard model of particle physics, and predict all the spectrum of superpartners, and then tell the experimentalists exactly where to look. Unfortunately, we are not that smart, so we'll have to do it probably in reverse, start from the LHC data, and reverse engineer this theory that breaks supersymmetry. So from this point on, I'll focus, this is the third part of the talk, where I'll talk about recent developments about supersymmetry breaking. So let me first set the scene. Yes?
Maybe you can say one sentence why it has to be broken spontaneously.
Okay. I'm glad you asked. In the context of supersymmetry, the symmetry has to be a local symmetry. Just like we have a gauge symmetry, which is a gauge local symmetry in electromagnetism, supersymmetry should also be a local symmetry. The reason for that is that, as I said, Q with Q is P. If I perform two supersymmetry transformations, I get translations. And we know that in the world, translations are like a gauge symmetry because it's part of the coordinate transformation. So just the fact that we have general covariance and we have coordinate transformation symmetry, supersymmetry, if it's there, also has to be a local symmetry. It has to be a gauge symmetry, and gauge symmetries cannot be explicitly broken.
Spontaneous breaking of symmetry, don't you expect that it would affect the distribution of the dark matter, that it would not be completely uniform?
The dark matter is not completely uniform. These particles are massive and they congregate around galaxies.
And are they scales?
Well, there's a whole theory of them, and they do simulations. It's not my field, but the dark matter is this idea of WIMPs seems to work extremely well. The cosmologists give you maps of where the dark matter is and what's the density of dark matter in various places. So what's the idea of spontaneous symmetry breaking? The Lagrangian or the Hamiltonian is invariant under the symmetry, has the symmetry, but the ground state doesn't. Here it means something very simple. So I said that Q with Q is P. One component of that is the two supersymmetry transformations, or kind of the square of the supersymmetry transformation is the energy, the Hamiltonian, or the generator of time translation. So if the ground state is not invariant, it means that the ground state energy is non-zero. So this is an example of a particle with a potential, or this is a field if it's field theory. And the ground state is when the particle is here. The ground state energy, as you can see, is non-zero, and therefore the ground state is not supersymmetric. So whether supersymmetry is broken or not, we can tell very easily, again in the language of statistical mechanics, the order parameter for supersymmetry breaking is the ground state energy. If Q kills the vacuum, does not kill the vacuum, the ground state energy is non-zero, and vice versa. So in this case, supersymmetry is broken. In addition, an idea first suggested by Witten is that the spontaneous breaking of supersymmetry is performed by a non-perturbative effect. In other words, we would like supersymmetry to be broken at very low energies, such that we explain why the W and the Z bosons are so much lighter than the Planck scale. How can we get this small hierarchy? In other words, how can we explain the aesthetic problem of naturalness? Where did this small number come from? Well, physicists know only one way of producing very small numbers. In fact, if you look at various examples, there's a unique way of producing very small numbers, and it's this one. You take a small number, g, which is not very small, and you compute e to the minus 1 over g squared, and that is a very small number. This is how BCS theory works. And the point about such a function is that if we expand it in a power series in g, it's 0 order by order in the power series. This function has an essential singularity at g equals 0. And therefore, if we compute in perturbation theory, we find 0 order by order. And then there is this tiny non-perturbative effect, which is very small because it's non-perturbative. And it's automatically much smaller, so this gives the mass of the W boson, much smaller than the Planck scale. So this was the idea of Witten put forward in the early 80s, I think around 81 or 82. And the idea was that there is some non-perturbative effect like that, very small effect, presumably a gauge theory effect, which will break supersymmetry, lift the ground state energy above 0 by a small amount. Eventually this will lead to the W boson, and we'll explain the hierarchy between the W boson and the Planck scale. So the general model of this class is as follows. We have the supersymmetric standard model. We have some other sector that breaks supersymmetry, and some interactions which couple the two sectors mediate the fact that supersymmetry is broken from here to here and lead to all the masses of the superpartners. And there are literally tens of thousands of papers analyzing this framework, and this is by far the leading candidate for what the LHC can uncover. So for the rest of the talk, I will ignore all that and just focus on that part of the story, how to break supersymmetry. It turns out to be much harder than expected. The typical example that we try to write down, we wake up one morning and say, well, let's find a theory that breaks supersymmetry. We write down some model. It does not break supersymmetry. Most models do not break supersymmetry. There are many constraints on supersymmetry breaking, and it's clearly not generic. However, the following twist makes things a lot easier. Consider a particle moving in such a potential. So first question, does it break supersymmetry or not? Well, clearly not, because the ground state is here. The particle sits here at the minimum. And here at the minimum, the ground state energy is 0. So this model does not break supersymmetry. So this is very much like the typical model that one would just write down. However, the potential has a feature here, and it could have a long-lived, metastable state here. If the particle sits here, doesn't know that there's another ground state over here. So the particle could be here for a very long time, and that looks as if supersymmetry is spontaneously broken. So if we allow ourselves a situation like that, we could live here, everything would look as if supersymmetry is broken, even though, strictly speaking, supersymmetry is not broken because the ground state is here, and supersymmetry is strictly unbroken. So this idea of metastable supersymmetry breaking, or that the universe is in a metastable state, has a very long history. I tracked it back to the early 70s in papers of Andre Linde and Steve Weinberg, but for all I know, it could be said long before that. Already in 82, Ellis, Llewellyn Smith, and Ross found an example where supersymmetry is broken in such a metastable state. Many examples of supersymmetry breaking in the 90s, originally with the work of Diane Nelson, show such examples. Again, metastable supersymmetry breaking. And there were some early ideas about supersymmetry, dynamical supersymmetry breaking in a metastable state by these people. And in 2006, together with two collaborators, we showed that dynamical supersymmetry breaking is actually very easy. It's very easy because the plot I presented on the previous slide with the metastable state is generic. Since then, many people have found lots and lots of other examples, and it looks like the generic model does the job. Means that you ask, what can a theory be? So a theory in particle physics needs some gauged fields and some quarks. So the simplest example that one would try is something just like QCD. We know QCD, let's do it again. So there's another theory which looks just like QCD, not to be confused with ordinary QCD. It has some gauge group and it has some quarks. That's the generic one. It turns out that this one already does the job. This is the first example you will try, and that's what I'll do in the coming slides. Any more questions on that? So this is the first example that we had, and it's actually very simple. Think of a theory like QCD, ordinary QCD. It has NC colors and NF flavors, very much like QCD, and it has some mass. These quarks have masses, again, very much like ordinary QCD. If the number of flavors is less than 3 times the number of colors, the theory is weakly coupled at short distance, but becomes strongly coupled at long distance. This is the phenomenon called asymptotic freedom, which lies behind the recent Nobel Prize for Gross, Wiltshire, and Pulitzer. The crossover scale between the short distance behavior and the long distance behavior is such an exponential small number, much smaller than the cutoff. So at very short distance, we formulate the theory. This is a theory like QCD. At very long distance, we get the phenomenon. And again, this is something that is being done all the time in statistical mechanics. At short distance, we have something like electrons and protons and nuclei and so forth. At long distance, we get, say, BCS theory, or we get superconductivity, which is described by effective degrees of freedom, which are different than the microscopic degrees of freedom. So the big challenge is always, given a short distance theory, knowing what we have at short distance, can we predict what the effective theory will be at long distance? And this is what a lot of the activity in condensed matter is all about, trying to find such a dictionary between short distance and long distance. So in this particular case, we actually know the answer. So this is a very complicated, nonlinear problem, strongly coupled, as complicated as possible, 4-dimensional field theory, which can actually be solved. And for some range of flavors and colors, the details are not important. This is the answer. So if we take a theory like ordinary QCD, make it supersymmetric, the potential as a function of some order parameter looks like that. So it has a minimum here, in fact several minima, so in which supersymmetry is not broken. So in this minimum, this is the ground state, supersymmetry is not broken. This satisfies a lot of theorems about the ground state. But ignore this state, there's another state here which is much more interesting. A state in which supersymmetry is broken, and we can use, simply because the ground state energy is non-zero, and we could use this point as the starting point for doing phenomenology for the real world. And we could very well live in a state which is just like this.
How long will
I'll come to that in a second. That's clearly a very important question. There are many other important questions. I'll come to them. So first of all, we have this complicated feature in the potential, in the effective potential, which is completely non-perturbative, completely quantum mechanical. Classically, we see no sign of it. Not only don't we see this potential, in fact, this order parameter along this direction is not visible semi-classically. So that's what I said. It involves directions in field space, these order parameters, which do not have a semi-classical meaning. And the potential is such that the lifetime of the metastable state is exponentially long. That's the answer to your question.
Exponentially what?
In the parameters in the problem. So we have some small number, again, doesn't matter what it is. Some the ratio between the mass of these quarks and the scale, the crossover scale lambda, and the lifetime is again e to the minus this ratio. So it's very easy to put numbers and make it much longer than the age of the universe. Say 10 to the 100th times the age of the universe. This is the lifetime per unit volume. So for phenomenology, this is perfectly safe. This is as if this thing is perfectly stable, and yet it satisfies all the theorems about quantum field theory are satisfied because they're satisfied in some other state, not in the state we are studying. This phenomenon appears to be generic, and many examples have been found. In fact, if you just write an ordinary field theory with any gauge group, any representation for the matter, you're going to find something like that. In fact, you typically have more than one such wiggle. So now I should take that and try and solve some of the problems in particle physics. So this kind of model, which breaks supersymmetry, can be used in some of the known mediation mechanisms, except that many of the problems and obstacles that people have faced in the last 20 or 30 years building such models are either easier or simply evaporate. So life is a lot easier in this setup. Mostly because we have many more models. Whatever model you write will do the job. In fact, the situation is inevitable. I'm not giving the details here, but if we just ignore gravity and we make very general assumptions about what the model is, we want spontaneous supersymmetry breaking, we want the theory to be generic so that no parameter is tuned to special values. We want the gauginos, the superpartners of the photon and the gluon, etc., to be massive, and we don't want massless bosons. That would contradict experiments. Every one of these assumptions is very, very mild. Then it necessarily leads to the conclusion that supersymmetry breaking happens in a metastable state. That explains why people had difficulties finding examples where this is not the case. So now we turn that around and turn that into a virtue. Such metastability is in fact inevitable, and I strongly believe that if supersymmetry is discovered experimentally, it will eventually tell us that the world we live in is metastable. There are other reasons for metastability, so I'm not operating in vacuum here. We know that the cosmological constant is non-zero. This is the statement of dark energy. I'll say nothing about that in this talk, but that tells us already that the world cannot be stable, the universe as we know it cannot be stable, mostly because it's very hard to make sense in quantum mechanics of the zero space. Also, in the context of string theory, many vacua were found of the order of 10 to the 500 when last counted. And so the potential really looks like a landscape with many different minima. And the last lecture here in memory of Yuval Neeman was given by Lenny, and I'm sure he did not miss an opportunity to promote this idea. But these are gravitational reasons. I said, forget gravity, set gravity to zero, set Newton's constant to zero. Even just in the context of particle physics and field theory, we have strong arguments that the world is in a metastable state. The counterpart of the question that you asked me about what's the lifetime of this state is the cosmology of this state. If we have a potential which looks like that with a metastable state, why do we find ourselves in a metastable state rather than in a stable one? Typically, we would say, well, we should live in the ground state, we shouldn't live in some excited state. Well, it turns out that life is a little bit more interesting than that. First of all, in general, whenever we are in a metastable state, there are new questions that have not been asked before, and we should address them. In particular, the thermal evolution of the universe. So at very high temperatures, when the temperature is much higher than any scale in the problem, it's clear that we are in the origin of field space. As the universe cools down, it turns out that there is a second order phase transition to the broken supersymmetry vacuum. This was shown by various people, including another of Tel Aviv's students. As the universe cools down further, the stable minimum, the lower energy state, comes down and becomes the lowest free energy state. There is a first order transition to this state, but that takes a long time. In other words, the thermal evolution of the universe puts us in the metastable state rather than in the stable one. How did this happen? Very roughly, in the metastable state, there are more particles, more light particles than in the stable one. So even though it has more energy, it has more entropy. So at very high temperature, it clearly wins over the stable one. Its free energy is lower, and the universe goes there. As we cool down, the balance changes, but by that time we have a barrier between the two minima, and we are stuck in the metastable state. So the cosmological evolution leads to the metastable supersymmetry breaking vacuum. So that's very appealing. There's nothing wrong with metastable states. In fact, this is where the universe wants to go, so it's quite possible that we are there. So for the future, we'd like to combine this idea with inflation. Maybe this potential that we derived so painfully can be useful for inflation. I don't have much to say about that. So these are the conclusions of my talk. So if you slept, this is the take-home lesson. And you will see it's very easy to remember. A few slogans and that's it. First, supersymmetry is the most conventional explanation for LHC physics. This is what most LHC physicists are looking for. Personally, I think that nature will surprise us and it will not be something we thought about. But of all the things that were put forward, this is the most likely one. So this is lesson number one. Lesson number two, if we accept metastability, we find surprisingly simple models of dynamical supersymmetry breaking. In fact, any model you write down does the job. The reason is that metastable dynamical supersymmetry breaking is generic in field theory and also in the landscape of string vacua. So that goes along with many ideas in string theory. The cosmology of this setup is interesting, and it poses new questions. New questions, some of them have already been addressed, others have not yet been addressed. So our goal is to find a good model for particle physics phenomenology. As I said, metastability is inevitable, so we'd like to find a model that really explains all of particle physics data, and we have to do it rather fast, because the LHC is going to come online very fast, very soon, and we hope that this model that we come up with will have clear experimental signals, and we'll make it as a prediction rather than a postdiction. So I think I'll stop here. Thank you.
Is there some generic prediction of metastable supersymmetry breaking that would be different than some other mechanism of supersymmetry breaking? Something that would be a smoking gun?
I don't have a quick answer. My hunch is that the answer is yes. And the problem is that we don't have a really fully satisfactory model that solves all the problems. If we had such a model, we could ask, what is the smoking gun, or what is the signal of this class of models? But I cannot give a smoking gun prediction without having a single example. So I'd like to have one example which does everything right, and then try and address this question. Having said that, near the top of my agenda is looking for generic predictions without having a model.
Describing the potential looks like a one-dimensional problem. And indeed, it's many-dimensional, and probably you have many ground states which have zero energy. And then the question is, it can go many ways. So do you really know that...
Yeah. So in this particular problem, first of all, the dimensionality of the potential is really infinite, because this is field theory. But even if you count fields, it's a multi-dimensional problem. And the nice thing about supersymmetric theories is that we can actually write the answer. We know what the function is. We have complete control over the problem. This is unlike the typical problems in condensed matter physics when you write a Hamiltonian, say the Hubbard model, and then there's a whole army of physicists trying to figure out what it does. Here we have exact formulas in supersymmetric theories. So we actually have control over the potential in all directions, and we know where all the minima are, and we can count the bounce action, which will tell us how long the lifetime is. I didn't do it in this talk, but it will be more than one colloquium to really explain how it's in.
Going from one to all of them.
From one to all of them. There is a small finite number of this potential was mapped out completely in all these models. And after you know how to do it, it's like a machine. It's really fast. And this particular problem has a small finite number of supersymmetric vacua, all very far from the origin in the relevant scale.
You've given us many examples of condensed matter physics. Therefore, I would like to ask the question, how useful is condensed matter physics in trying to think about things intuitively? Very useful. In fact, I took many body problems from you, and this course was very helpful.
Are there other questions?
I think Wilson was strongly motivated by condensed matter when he made fundamental contributions to particle physics. I don't think there should be any conflict between particle physics and condensed matter. I think there's only one science. There shouldn't be any conflict between mathematics and physics and chemistry and physics. It's only one science. We all have the same goal. And many times, good ideas in one field help the other. And conversely, if we have a good idea in one field, we should try and find good applications in the other field.
Shmuel, you have a question?
I just was wondering, this time, he was worried about the time, and you say it would be e to the -1 over g squared. There's no volume element, don't you have to tunnel the whole wall?
No, you create a bubble. That's a standard problem. In condensed matter, this was Langer. In particle physics, this was Coleman. You create a bubble, and these formulas are the decay probability per unit time, per unit volume. Yeah.
So maybe one last question, please.
Is there a danger that the LHC won't answer any of these questions? And if so, what will need to be the size of the next accelerator?
Okay, there is clearly a danger. It's a very serious question of whether the LHC will answer the questions. The real more precise version of it is, will the LHC answer any question? There is a danger that we will turn on the machine and we'll find, say, only the Higgs, or maybe we won't find anything, and we'll be as confused as we are today. That's true for any experiment that we do. There is never a guarantee in science, and that's a very serious... Sorry?
That's very valuable information.
That's also very valuable, exactly, but it would be extremely sad if that turns out to be the case. And the question is whether we have to pump up the energy. Yes, we'll have to ask ourselves this question, but my sense is that in the near future nobody will pay the bill for it. So it would be somewhat obsolete. However, if the LHC finds anything, I'm sure it will be very exciting because it will address questions like the origin of mass, most of the mass of the universe, extra dimensions of space. These are really fun, very exciting. Here I'm saying that the LHC could tell us that the universe is in a metastable state. They're really very exciting things that I think are very easy to explain to the general public. And even if the LHC addresses only one of them, I think it would be very easy to get the funding for the next machine. Zvi, you had a question.
Yeah. I would just like to bring this back to Yuval, because when Yuval came out with this SU3 theory, the particle physicists thought it was nonsense. And it was the nuclear physicists who at that time were considered to be dirt physics by the particle physicists, who saw that there was something in this SU3 that could be connected with experiment. And that's how our work started here.
So I think we would like all to thank Nati very much for the beautiful lecture. And if I may say so, I think if you were with us today, you would be very happy that Nati would. So thank you very much.